Today's lecture, which is 16th in the series on statics, will be discussing stability of equilibrium. You may recall that yesterday we were considering in lecture 15 we were considering the equilibrium of a system of particles and rigid bodies which is subjected to only conservative forces, and the characteristic of that system was that we could introduce the important concept of potential energy, and for equilibrium the condition for equilibrium is that the first variation of the total potential energy, which may consist of gravitational energy or elastic energy. So, the first variation is 0, okay, del V is equal to 0, and the equivalent condition for a system of n degrees of freedom, let us say q1, q2 up to qn, is that the derivative, the partial derivative of total potential energy with respect to each of these degrees of freedom q1 or q2 or up to qn equal to 0. Now, next important aspect to be examined is that once we have established equilibrium of the system, is this state of equilibrium stable or not? By stability or otherwise we mean that if we disturb slightly the configuration of the system, will the disturbance grow or it will attenuate, that is system comes back to its original equilibrium configuration. So, these questions are to be addressed and answered today. To motivate this discussion, I will consider a very simple example. Suppose we have a ball or a sphere lying on a curved surface. In one case the surface is concave, the other is convex, third is level surface, and fourth changes from convex to concave at a point. So, that is a kind of inflection surface. Now, in all these four cases you can see that the slope to the surface is 0 at one point, that is this point where x is equal to 0, y is equal to 0, similarly over here and over here. Now, suppose let me examine this case 1, I disturb it either to the right or to the left. Now, the ball will tend to come back to x is equal to 0, y is equal to 0 state. Okay. It will come back to the configuration of equilibrium. In case 2, if I disturb it slightly either to the right or to left, the disturbance will grow. It will go further and further away from the from this x is equal to 0, y is equal to 0 point, that is from equilibrium state. In the case 3, whether I disturb it to the right, to the left, neither the disturbance grows nor it attenuates, that is the ball will or sphere will stay in the disturbed position. Okay. And in 4, if I give a disturbance to right, well, it will have a tendency to come back, but it may overshoot that position and then it will go into a mode of growing disturbance. So, this also is to be treated as a kind of growth of disturbance case. Now, let us say there is only gravitational force acting on in each of these cases. So, the height of the CG of the ball is a measure of the potential energy. Now, in this state, well, the CG will be at this position, and when I disturb it, CG will rise and then it will come back as the ball tries to come back. So, it means that for equilibrium, the potential energy is proportional to the height of the ball. Okay. So, when dy by dx is equal to 0, that is the slope is 0 over here, it means the potential energy is also dV by dx equal to 0. That is precisely the condition for equilibrium. So, in all four cases, from the principle of stationary value of potential energy, we see that these are the cases of equilibrium, but we have the four cases as we have discussed. And what is the distinguishing feature between of all these four cases? In case 1, the curvature is positive. You can see it is a concave configuration surface. So, if I consider the curvature over here, that is rate of increase of the slope, that is positive. Curvature is nothing but rate of increase of the slope. In this case, rate of increase is negative, because here slope is 0 and then it becomes lesser and lesser. So in case 1, the curvature is positive. In case 2, curvature is negative. In case 3, curvature is 0, it is a flat surface. And in case 4, there is a non-definite curvature, that is positive as well as negative, and at the middle point it is 0. So, it is a case of change of curvature according to the place value of x. Okay. Since we have already said that the potential energy is proportional to the height of the ball, so it means for the, if we rephrase our conditions in terms of potential energy, then we will have the following conditions. That is, if the second derivative of the potential energy with respect to the variable is positive, then the system will be stable. If it is negative, the system will be unstable. So, we will examine from that point of view the stability of equilibrium. Conditions for stability of equilibrium. First of all, we will take up 1 degree of freedom case, that is just like the case we have examined a short while ago. So, let V be the potential energy of the system with 1 degree of freedom, and x is equal to x0 be the state of equilibrium. So, it means when x is at x0, the system is in equilibrium, and now we give a small perturbation or disturbance delta x from the state of equilibrium. So, we will define the disturbed state by x and the equilibrium state by x0. So, x minus x0 is the disturbance or perturbation delta x. The potential energy of the system is the function of the variable, that is function of that degree of freedom which we are calling x. So, Vx, that is the potential energy in the state x, that can be expanded in a one dimensional Taylor series around point x0, that is the equilibrium state. So, by Taylor's expansion, we have Vx is equal to V at x0 plus dV by dx evaluated at x0 times the disturbance delta x plus 1 by 2 factorial, second derivative of V with respect to x evaluated at x0 times the disturbance square plus 1/3 factorial, third derivative evaluated at x0 times the disturbance cubed plus higher order terms. It is an infinite series. Now, look here, this is the potential energy at the equilibrium configuration, and at equilibrium configuration we have already established that the first derivative, that is the slope, is equal to 0. So, the first term at equilibrium vanishes, okay, and I take Vx0 on the opposite side. So, then we will see what happens. If we call the change in potential energy del V equal to Vx minus Vx0, okay, that is the difference of the potential energy between the perturbed state and the equilibrium state. So, that is del V. Then del V is equal to 1 over 2 factorial second derivative of potential energy with respect to the degree of freedom evaluated at equilibrium configuration times disturbance square, and then the third order term, fourth order term, and so on and so forth. Now, since delta x is very small, well, delta x square will be even much smaller, but delta x cube, delta x4 will become much smaller. Okay. So, in this series the largest term or the dominant term is the first term, okay, and since delta x square quantity is always positive, whether disturbance is positive or negative. So, the sign is immaterial. So, it means del V, the change in potential energy, will be dominated by this factor. So, this is the dominant term. So, we will look at the behavior of the second derivative of the potential energy at x is equal to x0. Just like in the example which I have given you, we were guided by the curvature d2y by dx square, that is also a second derivative. So, here for a general system, conservative system having a potential energy V, we will be again guided by in deciding the stability of equilibrium by the second derivative of the potential energy at the state of equilibrium. Well, when we have the first case, this term, that is the second derivative, is positive, it means that the perturbation causes an increase in V, therefore, the potential energy is minimum at x0. Okay. So, when the second derivative is positive, you come back to the figure here. So, when I give a disturbance on this side or in this side, the height increases in both ways. So, it means that the equilibrium state is the lowest point. So, similarly, in our case of potential energy of 1 degree of freedom, the first case corresponds to the minimum value of the potential energy, because any disturbance either to left or to right will cause an increase in the potential energy. When this second derivative is negative, okay, then it is parallel to the case 2, where whether you go to the right or left, the ball is going to a lower position. It means your potential energy is decreasing by analogy. So, it means this is the case of maximum potential energy. So, that any disturbed position will be lower, will be having a lower potential energy. And when we come to the third condition, that is the second derivative is 0, then it is a level case. It means potential energy neither increases nor decreases, okay, at that point. So, in that case, either the potential energy is constant, or at best you go to the third order derivatives, that is del cubed by V by dx cubed, okay. So, we go to this term, evaluate at the equilibrium state. So, then you have to decide whether this term is positive or negative. If it is positive, you have a tendency towards stable equilibrium. If it is negative, again you will have unstable equilibrium. So, that was for 1 degree of freedom. The analysis was very simple, that all you have to do is compute the second derivative of the potential energy as a function of that degree of freedom. Now, when you go to 2 degrees of freedom, then the situation is more complex. Well, for equilibrium, we know that let us say x and y are 2 degrees of freedom, or q1 and q2 are 2 degrees of freedom. I am using x and y. Then for equilibrium, since the first variation is equal to 0, it means that the partial derivatives of the function v potential energy function v with respect to x or with respect to y, both are equal to 0. That is the condition of equilibrium. Okay? And then to see whether our equilibrium is stable or unstable, we have to first consider, well, there will be second order derivatives d2v by dx square, d2v by dy square, and the mixed derivative d2v by dx dy. So, first you consider this expression, that is the mixed derivative squared minus the second derivative with respect to x square x multiplied by the second derivative with respect to y. That quantity, when you evaluate this expression, should be negative. That is condition number 1. And then the sum of the second derivatives d2v by dx square plus d2v by dy square should be positive. Okay? This is incidentally called the Laplacian. Laplacian of v is positive. So, as I said, for stability, first we ensure that it is a state of equilibrium, and then these two conditions have to be simultaneously met. For the case of instability, then again we have the condition that it is a state of equilibrium, that is understood, and then this condition is same as in the previous case for the stable equilibrium case. But the Laplacian, the third condition, Laplacian condition, is opposite. In the previous case we had this quantity as positive, now it is to be negative for unstable equilibrium. Okay? And again, if it is equal to 0, that is, it is neither positive nor negative, then you have to go to the higher order derivatives, and then the system becomes, and then the set of equations becomes more complex. Similarly, if you have more than 2 degrees of freedom, q1, q2, q3, then the analysis of stability when the relevant equations become much more complex, because then you will have so many derivatives to worry about. So, we will, for most of the cases, we will concentrate on 1 degree of freedom. I will take up 1 or 2 examples of 2 degrees of freedom also. So, to sum up, if you have a system comprising of particles and rigid bodies, which is subjected to only conservative forces, no dissipative forces like friction or some other viscous dry friction or hydrodynamic friction, lubrication, etc. So, no such components are involved, then the system can be examined in terms of the potential energy and the stability criteria of in terms of the second derivatives of potential energy has been set up. Let us go to some examples. First of all, I consider a very simple example. Here is a plate, a thick plate, which is having a kind of a nose which is circular in shape. So, let me, a thick plate whose bottom edge is that of a circular arc of radius r. So, this is shown here, the center of gravity of the plate is at a distance h from the lowest point, that is the point where it is resting on the floor, level floor. When the plate is in a vertical position as shown in the diagram, what relation must be satisfied by h and r for stable equilibrium? So, first of all we will have to consider when is the equilibrium obtained, and then examine whether equilibrium is stable or unstable, right. In all these problems you start with a disturbed position, okay, and then we will see under what circumstances that position will be an equilibrium position. So, this is what we are going to do. Here I have given a disturbance, so that is I have gradually tilted this plate, and in tilting the plate is being tilted without slippage, that is always one point of the lower edge was in contact with the floor as shown here. So, now in the tilted position theta is the angle which the center line of this is a symmetrical body, the center line of this plate makes with the vertical, and theta is incidentally the degree of freedom, because once you prescribe theta you can see its inclination, and that is sufficient to establish the configuration of this plate. So, this is a system of 1 degree of freedom. Now, there is no other force except gravitation force, all right. So, it means I have to calculate its potential energy in the disturbed configuration. This is the center of gravity of the plate, right. So, it means how high I will take. First of all, I think right in the beginning, first of all you have to decide two things. How many degrees of freedom? We have seen that there is only 1 degree of freedom, and what is the datum for, if it is a conservative system, what is the reference point for zero potential energy or datum. We will take the floor, that is the lowest point of this body, as the datum, and we call the potential energy equal to 0 at that point, at that level. So, this is V is equal to 0 state, that is when it is just touching the floor. So, Cg being at a height, well, in the vertical position it was at a height h. Now, we have to find out the Cg, the height of Cg. Obviously, this is r, the radius of the nose, and you can see that this thing is this is total r. So, r minus h, this is r minus h, okay. This is also radius r. So, the depth of the Cg along the center line from this center of curvature of the nose is h. So, is r minus h, and to find out the height of this Cg, it means this r, this is the vertical line, minus this height, this is r minus h cosine theta. So, this is r minus h angle theta. So, this will be r minus h cosine theta. So, r minus h cosine theta, that is the height of this Cg. Okay. So, from the datum the potential energy is W is the weight of the plate. So, W into R minus R minus H cosine theta, that is the potential energy in the disturbed configuration. Let us take the, for equilibrium, the first variation is equal to 0, or which is equivalent to this statement that dV by d theta, because there is only one degree of freedom, is equal to 0. So, when I differentiate it, you will have first constant 0. So, r minus h sin theta. So, dV by d theta will be r minus h sin theta, and this is set equal to 0 because r minus h is not 0. So, it means sin theta is equal to 0. So, one simple root of this is that theta is equal to 0. So, it means there is no inclination, the plate is standing vertical. This is the state, that is the plate is the line of symmetry is vertical line. Okay. So, that is the state of equilibrium. Now, we want to establish whether this equilibrium is stable or unstable. For that, we will now take up the second derivative. So, again it is easy to calculate, it will be r minus h cosine theta, and when theta is 0, that is at the state of equilibrium. So, it means second derivative at theta is equal to 0 is simply r minus h, because cosine of 0 is 1. So, for equilibrium for stable equilibrium, this quantity has to be positive. For unstable equilibrium, this quantity is negative. Positive means r minus h is greater than 0 or r is greater than h. So, if the radius of curvature is larger than the height of the CG from the lowest point of the plate, then you have a stable equilibrium. If on the other hand the radius of curvature is lower than CG, that is r is less, that is here I have shown the center of curvature is above the CG, that is a stable configuration, because then r, this is also r is greater than h, but if r is over here, that is the nose is very curved, radius is smaller, then the equilibrium is unstable. Okay? And of course, if r is equal to h, then we have to examine the higher order derivatives. So, this is exactly what we have concluded, and now I will take up another example. Well, this example was in fact discussed in the last lecture, lecture 15, where we were only concerned with the equilibrium configuration. We did not pay attention to the stability of equilibrium. You may recall that there is a heavy rod which is pinned at one end, and the other end is going through a string over a pulley and carries a mass m. Okay? And then we wanted to find out whether when theta is equal to 20 degree, what is the value of m which will maintain the equilibrium of this state. When we were solving this problem, we set up the potential energy, because there is only gravitational force involved, all forces are conservative. So, potential energy is easily defined in terms of the potential energy of the rod as well as that of the mass. And if you recall, we had set up this expression in our last lecture for the potential energy. V is equal to 73.6 cosine theta minus 9.81 into mass m divided by 2 into 1.92 minus square root of 3.69 minus 3.6 sin theta. Okay. So, and when we took the first derivative equal to 0, then we came to the conclusion that if our value of m, that is mass is 6.54 kilogram, then the body was in equilibrium for theta is equal to 20 degrees. That was the result obtained just last time. Now, for stability we will take the second derivative. Okay. Again it is very simple to take the second derivative. Cosine theta will give me minus sine theta, and then this expression you will find this is the derivative, and after simplification when theta is equal to 20 degrees, that is you substitute theta is equal to 20 degrees and m is equal to 6.54 in all these calculations, you will find that the second derivative comes out to be 47.6, which is greater than 0. It is a positive quantity, hence it is greater than 0. Okay. So, it means this configuration of theta is equal to 20 degrees and m is equal to 6.54 is a stable configuration. So, that if there is a small disturbance, that is mass slightly vibrates up and down, the equilibrium will not be disturbed forever. It will come back to the disturbed configuration will be such that it will come back to equilibrium. That is the interpretation of stable equilibrium. Let me take up an example where we will have two types of potential energies, and this example is let me read out. A weight W is welded to a light rod. This is rod AB is a light rod, let us say made up of aluminum or some polymer, and W is sitting on it, rigidly connected to it. The length of the rod is 1.5 meter, and at the lower end of the rod there is a torsional spring, just like in your watches. So, this torsional spring is trying to, if there is a tilting of the rod, it will try to bring it back to the vertical position. Just like your linear spring, if you disturb it, it brings the disturbed end back to its, tends to bring it back to or restores it to the equilibrium. So, similarly here, if you give a disturbance, angular disturbance, then it comes back, it tends to come back to its original configuration. And the stiffness of this torsional spring is naturally in terms of moment, restoring moment, Newton meters per radian, per angular disturbance, unit angular disturbance. So, 250 Newton meter per radian. The spring is linear and unstrained when the rod is vertical. So, he has defined the datum for the spring. That is, when it is vertical, the spring is untwisted, that is, it is in a natural configuration, and hence the potential energy is 0. What is the largest value of W for which we have stable equilibrium in vertical direction? So, what is that W which is slightly increased will cause unstable equilibrium? That is the interpretation. Well, as I said, we will have, first of all, we will fix the datum. Two types of energies are involved, the potential energy of the weight, because the rod is light, so we will neglect whatever potential energy of the rod is there. And second potential energy is that of the spring, elastic potential energy due to rotation of. So, the 0 state, that is the vertical state, is the 0 state of potential energy of the spring, and this is the datum for the W. Second thing we will do is that we will disturb the system through an angle theta. So, I will take anticlockwise positive. So, I have disturbed it to angle theta, and weight will be now acting over here, and we will find at what height the weight is now, so that what is the potential energy of the weight. First of all, the elastic potential energy of the torsional spring is half kT theta square, just like we have for linear spring half kx x square. So, similarly for the torsional spring you can exactly in the same manner prove that the potential energy of the spring is half times this torsional stiffness kT of the spring times angle of rotation square. Okay. And the total potential energy of the system will be W into the height, its height, that is the weight times the weight times the height. Originally it was over here, so it has gone like this. So, it means this length is 1.5, the length of the rod, into cosine theta, that will be the vertical intercept. So, that is the potential energy of the weight, plus half 250, that is the torsional stiffness of the spring, theta square. All right. So, this is the total potential energy, and if I differentiate it and set it equal to 0, that will be the state of equilibrium. So, that is a very simple step. So, cosine theta will give me minus sine theta and this will give me 2 theta. So, I get this expression, and one root is obvious, that is when theta is equal to 0, this term is 0, this term, so 0 is equal to 0. So, it means theta is equal to 0, that is when the rod is exactly vertical, that is a state of equilibrium. Now, we have to examine whether this equilibrium is stable or not. So, what we do is take the second derivative. So, sin theta will give me cosine theta and this will give me just 250. So, you will have minus 1.5 W cosine theta plus 250, and since theta is equal to 0 for equilibrium, so it means minus 1.5 W plus 250. And since for stability of equilibrium we want that this should be greater than 0, positive, it means, well, this is a negative term, so we can take it on the opposite side. So, 1.5 W is less than 250, or W should be less than 250 over 1.5, which is 166.67 newtons. So, as long as the weight on the rod is less than this, we will have stable equilibrium. As soon as it exceeds, we will have unstable equilibrium. So, you imagine that here is a rod, I am slowly increasing the weight sitting on it, and up to 166.67 Newton weight, the rod is straight vertical in a stable manner. As soon as this limit is exceeded, the equilibrium becomes unstable, not that it will immediately collapse. What it means is that if I give a small disturbance to the rod, this disturbance will grow and immediately the rod will fall down, and hence the weight will fall down. So, W is equal to 166.67 is the critical weight, and similar problems arise in many other situations. One important thing is about structures. So, in structure, let us say columns, etc., they can withstand certain weight, and if that weight is exceeded, the columns buckle. So, as you will be learning in solid mechanics courses later on, you will see that buckling or a straight column becomes a curved column. That phenomena is a phenomenon of instability, and which happens for long thin columns subjected to compressive loadings. So, this example is very useful in understanding instability phenomena. Let me take up another example, which is a very interesting example. Here is a homogeneous block of weight W which rests on a dome which is in a form of a semi-cylinder, and show that this condition is unstable if h, this height of the block, is greater than 2r, that is the diameter of this dome, or twice the radius of this dome. Well, again we have only one type of force, that is the gravitational force. So, it is a conservative system. We will work with the potential energy and we will treat this level, this ground level, as our datum for potential energy. That is, the potential energy of the block will be measured with respect to, or the height of the CG of this block will be measured with respect to this floor on which this dome is fixed. Okay. So, as usual, we will disturb the system through an angle theta. That is, again, while tilting this block, we have to bear it in mind that at no stage there is slip taking place. That is, this tilting is without slippage. So, that this length is equal to r into theta, this radius r into theta, that is arc length. So, this arc length is this length, and by parallelogram this is the length. Okay. So, that is very important, that is, any tilting or disturbance should be without any slippage, that is, the contacting points are always at rest with respect to each other. All right. Now, rest of the problem is actually almost a problem of trigonometry, because this is the CG of the block. I have to find out the total height y of the CG, which consists of the r plus h by 2 is this total from this point to this point, okay, and then this length is parallel to this. So, this is, since due to no slip condition, r theta is the arc length. So, that this length is also r theta, and hence this length is also r theta. So, that this difference, because this will be r theta sin theta. Remember that the angle here is also theta. Why it is theta? Always remember that the angle between two lines is equal to angle between their normals. So, the angle between r and this vertical is theta. So, horizontal line is normal to the vertical, and this line is normal to this radial line. So, it means this is also angle theta. Okay. So, this is r theta, angle is theta. So, vertical distance will be r theta sin theta. Okay. And the vertical projection over here is r plus h by 2, this is the total length r plus h by 2, r plus h by 2 into cosine theta. Okay. So, the total height from the figure is r plus h by 2 cosine theta plus r theta sin theta. So, once again, this evaluation is simply trigonometry and geometry of the figure of the problem. So, after having understood it, then the matter is very simple. The height of the CGY is r plus h by 2 cosine theta plus r theta sin theta. So, the total potential energy of the system will be the weight of the block. It is supposed to be acting through the CG. So, W is the weight of the block times y, that is r plus h by 2 cosine theta plus r theta sin theta. So, after having established the potential energy of this system, let us examine the equilibrium, that is dV by, this is a system of 1 degree of freedom only, dV by d theta is equal to 0. Well, once you have dV by d theta equal to 0, rest is simple derivative of this expression. So, you can easily see that cosine theta will give me minus sin theta, and this will give me two terms, first differentiation of theta and then differentiation of sin theta. So, these are the two terms, and this is to be set equal to 0. After little simplification, because you can see minus r sin theta will cancel out r sin theta here. So, minus h by 2 sin theta plus r theta cosine theta is equal to 0. Well, there is a theta here, there is a theta here, and cosine 0 is 1. So, obviously, theta is equal to 0 is a root of this equation. It satisfies this equation, hence it is the state of equilibrium. So, what does that mean? Theta is equal to 0, it means that this configuration, when you have block sitting on the highest point, so that this is vertical. Okay. Now, let us examine the stability of our system. Again, take the second derivative. We will have second derivative from the previous expression, once again differentiating it, then set theta is equal to 0, because that is the state of equilibrium. So, we will have after setting equal to 0, this will be 1, this will be 1, this will be 0. So, minus W into h by 2 minus r, right. And if this quantity is positive, or take the negative sign on the other side, if this factor is negative, then the equation is then the system is stable, and so on and so forth. So, the block is unstable when h is greater than 2r. So, h is greater than 2r means this will be positive and the derivative will be negative. So, this is the condition for instability of the equilibrium, and if it is h is less than 2r, then the system will be in equilibrium. So, I think with these examples we have seen how to examine or how to analyze whether a given state of equilibrium is a stable state or an unstable state. Okay. If it is a stable state, it means that a small disturbance, I am not talking of large disturbance, so that the system will go into an entirely different mode. So, I am talking about only small disturbance, whether it will grow or it will attenuate. If the and we are talking of only the conservative system, and if the second derivative is positive, then it will attenuate, the disturbance will attenuate and system is stable. And if it is negative, then the disturbance will grow and system will be it will leave the equilibrium configuration after a while and it is unstable. Okay. So, these methods which we have discussed, the potential energy method and virtual work method, as I have emphasized in the beginning and I will like to emphasize once again, they are very robust, very powerful methods, not only for mechanical systems. Actually, similar procedures have been applied in many other systems, electrical systems, thermal systems, etc. And the basic concepts are exactly on the same lines. That is, we define a potential function, may or may not be a mechanical potential, sometimes even chemical potentials, electrical potentials are discussed. So this simple analysis is the starting point of stability in many contexts, and that's why you must understand these concepts fully, and they will be useful in many problems. So this was the last chapter or last lecture in this statics part of the course on mechanics. If we recapitulate in next 5 minutes what we have learnt in these 16 lectures, well, in the first 1 or 2 lectures we were discussing about the preliminaries, mathematical preliminaries. Mainly we were discussing the vector analysis, because you might have realized that throughout we have used vectors, and we have used them very profitably, very economically, and I hope you will continue to use vectors in your higher courses also. And then we came to description of what are the various simplifications or assumptions made in particle mechanics. I have not discussed rigid body mechanics as a separate entity. So what are various types of forces? Then we were also discussing about the basic laws of mechanics, Newton's laws. Secondly, Stevinus laws, which established that force is a vector quantity, etc. And we had some discussion on equivalent force systems. That is, a given set of forces and moments were replaced by the simplest possible force system. Force system means forces and moments. Okay, and then we came to the concept of equilibrium of forces acting on a particle or on a rigid body, right? And for a system of rigid bodies, it was essential to break up the given system into smaller systems or subsystems in terms of free bodies, and all the contact points were replaced by the reactions, which can be force reactions or moment reactions, and then we applied the conditions of equilibrium. Using those concepts, we went into structural mechanics, where we applied the concepts of free body as well as the equations of equilibrium to trusses as well as beams. Okay, we found out in case of trusses, we found out the forces in trusses and the reactions from these supports. In case of beams, we derived the shear force distribution and bending moment distribution along the length of the beam, and this led to shear force diagram, bending moment diagram, etc. Finally, there was another useful application of these concepts, namely in case of friction. For a system having friction, friction was identified as a force which tries to prevent motion, and if the motion is already taking place, it hinders motion. It appeared to be a kind of unwanted force, but then there were very technically useful applications of friction, namely in thrust bearings, in belt and pulley drives, etc. And we examined those cases in detail, solving several examples of practical application. After discussing friction, we came to the properties of moment, properties of surfaces, namely the first moment of an area, second moment of an area, the centroid of an area, etc., and then we came to a parallel concept, that is the moment of inertia and product of inertia. Although we have not made much use of moment of inertia and product of inertia, but they will be very much needed when you go to dynamics of rigid bodies in this second module, that is the dynamics. Okay. So, there you will be needing it. Also in higher courses, solid mechanics, etc., the second moments of area and the first moment of area will be needed in the theory of beams, a very important application of solid mechanics. And finally, we came to the principle of virtual work, which provided us with the alternate method of analyzing the equilibrium, but it was restricted to some constraints, that is let us say a particle is moving on a surface which is a smooth surface. So, all the dissipative or friction forces were left out of consideration. So, if all the active forces are non-dissipative, then the equilibrium can be examined by applying certain virtual displacements and computing the work done during those displacements and setting equal to total virtual work equal to 0. The advantage of that method was that unlike forces and moments, which are vector quantities, work is a scalar quantity. So, the work contributed by several particles or several forces can be simply added or subtracted. Okay? And secondly, the problem of mechanics can be almost reduced to that of trigonometry or geometry, and hence the analysis becomes very simple. No internal reactions need to be taken into consideration, only outside active forces, whether it is for a particle or for a rigid body. And when these forces further happen to be conservative forces, then it is very advantageous to use the concept of potential energy, because conservative forces mean the work done by any path is same, right. So, and the final advantage of the method of potential energy was that we could examine the stability of the system in a very natural and simple way. This is what we have discussed today. So, with this I close this module on statics, and somebody will be taking up the next part on dynamics. Thank you very much.